Hey, Honors Ken, Mr. Lambert here. Let's get into limiting reactants. Before I talk about this, I want to show you this little button here. This is my headset with a mic mute button and a volume control. And even though this is the first time this video is being published, it's the second time I've recorded it because after 11 minutes of video recording, I realized that this switch somehow, because it's down below where my legs are, got switched off. So I'm not in a good mood, but we are going we're going to enjoy limiting reactants. And this is one of my favorite parts about teaching chemistry and understanding the concepts behind how chemicals react. So hopefully this will help. Just as a reminder, we are in Lesson 9, Chapter 9, Section 9.4. It's going to cover pages 258 to 262. It is limiting reactants. Before we get into any calculations, I want to make sure all of you students understand the concept behind limiting reactants. What does it mean? A limiting reactant is a chemical that is going to run out first in a particular reaction, because as you know, in most chemical reactions, not all, but most, you need more than one reactant, but one of them's going to run out first. So in your book, it talks about a real life example that doesn't deal with small amounts of matter uh, in a chemical reaction. It talks about going to a picnic. Let's say you're going to a picnic with a bunch of friends and you have the following. These are your reactants. These are the things that you're going to be giving to your friends. You have 10 spoons, 8 forks, and 6 knives. However, each person requires one of each in order to eat. How many people can eat? How many people can you feed? Well, as you know, you don't have the same amount of each of these utensils. So it's the knives, not the spoons or the forks, but it's the knives that's limiting the number of people that can eat. This would be what's considered the limiting reactant. So how many people could actually eat? If each person requires one of each, you can only feed 6 people. Let's take a look at a chemical reaction and we'll try to figure out the limiting reactant. So here we have a chemical equation with 2 reactants and 1 product. I want to make sure everyone's aware right off the bat that this is a balanced chemical equation. The mole to mole ratio is a 1 to 2 to 1. What are the reactants? What's the product here? We have CO, carbon monoxide gas. That's our first reactant, plus H2, 2 moles of H2. Hydrogen gas will yield what's called methanol. This is methyl alcohol, CH4O. Here is the question. It's sample problem 9.7 on page 259. What we have is 3.00 moles of CO. We have a certain amount, 3 moles of carbon monoxide. And we have 5 moles of H2, 5 moles of hydrogen gas. If those are the amounts of our initial reactants, what is the limiting reactant and how many moles of methanol can be produced? We're going to try to answer 2 questions here, sort of at the same time. In a previous video, we talked about going from grams of one chemical to grams of another, or moles of one chemical to moles of another. We're going to do the same thing, but in this particular case, you're going to get information about each reactant. You're going to get a measurement of each one, and it's our job to figure out which one runs out first. So we're not doing anything different than what we've been doing. We're still going to be doing grams to moles, moles of chemical A to moles of chemical B. It's just a little bit longer this time. We need to figure out which chemical runs out first. First off, you might be thinking, well, wait a minute. If I have 3 moles of this, and 5 moles of this, 3 is less than 5, so this must be the limiting reactant. This must be the chemical that runs out first. Not so fast. Think about mole to mole ratios. For every 1 mole of CO, we could produce 1 mole of methanol, CH4O. But for this right here, for every 2 moles of hydrogen gas, we only get 1. So there's going to be a difference. We need to use that mole-to-mole ratio. What I'm going to do is I'm going to show you how to calculate this, jumping from moles of each of the reactants separately to moles of the product. I'm going to reiterate that. 2 different hypothetical, theoretical calculations, jumping from moles of each reactant to moles of the product. There's only one product in this case. So the 3 and the 5, whereas the 3's there, the 5's there, they're going to be used. I'm just going to erase this and pause the video so I can show you the calculation. Once again, 2 separate calculations. Here we go. We're going to, let me do this. I'm going to do 3.00. That's how many moles of CO we had, or we have, and then we have 5.00, make those big enough, moles of H2. Let's start with this reactant. We're going to jump from here to here and see how much we could produce if we used up all 3 moles. We're not even going to worry about hydrogen right now. That's going to be a separate calculation. We're going to go like this. 3.00 moles of CO. Make sure you label. That's important. I know I'm writing with an upward slant, but I'm trying to make sure everyone can see here. We're going to jump from moles of CO to moles of methanol, CH4O. So I'm going to bring this down so I can cancel out the unit. Moles of CO on the bottom, moles of CH4O. Bring that line over on the top. What's the mole-to-mole ratio? If we're jumping from here to here, moles to moles, it's a 1-to-1. No coefficients in front, it's a 1-to-1. So what are we really saying? We're saying that if we react 3.00 moles of carbon monoxide, we could, in theory, produce, it's a 1-to-1, 3.00 moles of CH4O. I am going to cross these out just so you can see the dimensional analysis. But that doesn't tell us much yet. If we have 3 moles of this, we could produce 3 moles of this. What about the hydrogen gas? We need to do a separate calculation down below. I'm going to start with the measurement of the other reactant, and we're going to see how many moles of the product we could produce. It is the reactant that produces the least amount of product. We're looking for the smaller of the 2 numbers. That would be our limiting reactant. We have not found our limiting reactant yet. Let's find out what it is and go from hydrogen to methanol. 5.00 moles of H2. We'll put that over 1. I got to move that so everyone can see. And we're going to jump from moles of H2 to moles of the product. Once again, moles of H2 to moles of CH4O. But check this out. In this particular case, the ratio is not a 1-to-1 because we're jumping from hydrogen to methanol. So there's going to be a 2 on the bottom here and a 1 on the top. For every 2 moles of hydrogen, there's 1 mole of methanol being produced. So essentially, we're going to take this number, this 5.00, and divide it by 2. I do have my calculator handy, but I would think most of you can probably figure out that 5.005 divided by 2 is going to be, to 3 sig figs, 2.50 moles of CH4 being produced. So what does that mean? That means, let's recap. If we used up all 3 moles of this reactant, we could produce 3 moles of product. If we used up the 5 moles that we had originally of this reactant, we could only produce 2.50 moles of CH4O. Once again, the reactant that can produce the least amount of product And the least amount, and again, moles are amount, the least amount of product, that's your limiting reactant. Which one of these two chemicals is the limiting reactant? Keep in mind, we went to the product in both cases. Let's go back and look at our reactants. The one that produces the smaller amount of product is the limiting reactant. What I like to do, and by the way, it's H2. It's hydrogen gas. Okay, this is the one that's going to run out first in this theoretical calculation. So what I like to do is I like to go back up to the initial equation, and I like to write above this reactant right here, which is our limiting reactant, I like to write LR, which of course stands for limiting reactant. We know that this is the one that's going to run out first. I'm going to stop the video, and I think I'm going to make a second part so these aren't too long. And we'll talk about going from grams of one chemical to grams of another, but we're going to have to do the separate calculations with each reactant to figure out which one could produce the least amount of product and therefore be the limiting reactant.